Welcome to Brain Vision.
Part A of this problem is asking to draw free body diagrams for both block A and block B. For block A, we have a normal force upward. We have a tension force to the right, I'm going to denote by T1. We have the weight of A downward, and we have the friction force on A to the left. For block B, which is sitting on the ramp, we have a tension force upward, T2, it's different than T1. We also have T1 downward. Now this is the same as this T1 because they're connected to each other. We have the normal force of B perpendicular to the ramp. We have the friction force of B opposing the motion down here. And we have the weight down here like this. Now, of course, we can split this up into its components like this. This becomes WB times cosine of 36.9 degrees, because that's what this angle here is. And this becomes WB times sine of 36.9. And I believe that's the answer to part A there. I think I've got all the forces. For part B, we want to figure out what T1 is, the tension between blocks A and blocks B. So the way we do that is we're going to first do the sum of the forces in the y direction, which is equal to 0 since there's no acceleration in the y direction. We're going to do it on A. And just to keep it straight, that's A and that's B. This implies that the weight of A equals the normal force, because those are the only two forces in the y direction, and they're in the opposite directions. Now we're going to do the sum of the forces in the x direction on A. And again, it's equal to 0, because although they're moving, they're not accelerating. And so Newton's second law there gives us that T1 is equal to the friction force on A. But the friction force on A can be expressed as the coefficient of kinetic friction times the normal force. We found the normal force here. It's equal to the weight of A. Now these are both given in the problem, and so we can easily calculate this to be 8.75 newtons. And that's the tension in the row between A and B. Now in part C, we want to figure out what the weight of block C is. And so the force diagram for block C looks like this. We have tension T2 because it's connected to block 2, going up like that. And we have the weight of C pulling it down. Newton's second law, the sum of the forces in the y equals 0 because there's no acceleration, implies that the tension in row 2 is equal to the weight of C. And so if we can figure out what T2 is, we'll have the answer, because we're trying to solve for the weight of C. So to figure out T2, we're going to look at block B, and we're going to take the sum of the forces along the ramp equals 0 because there's no acceleration along the ramp. This is again for block B, gives negative friction force of B, because pointing in the negative direction, minus T1 minus the weight of block B times sine of 36.9 plus T2 is equal to 0. Solving for T2, this gives T2 is equal to T1 plus weight of B times sine 36.9 plus friction force of B. Now we want to figure out what this friction force of B is. And in order to do that, we're going to do the sum of the forces perpendicular to the ramp. It's equal to 0 because there's no acceleration in that direction. And this equation implies that the normal force of block B is equal to the weight of B times cosine of 36.9. Well, we know what the weight of block B is, so we can easily calculate the normal force here, and it's equal to 20 newtons. This implies that the friction force of B is equal to 0.35, which is just the coefficient of kinetic friction they gave us, times the normal force. And this gives us 7 newtons. So now we know T1, we calculated in part A. We know the weight of block B. This is just sine of 36.9, and we just calculated the friction force of B. So we can solve easily for T2. And when we do that, we get 30.76 newtons. And again, this implies that the weight of C is equal to 30.76 newtons. And that's the answer for part C. Now for part D, we're cutting the rope between A and B, and we're trying to find the acceleration of block C. So now if I redraw my force diagram for block B, I get tension T2 moving up like that. I still have my normal force in this direction. I still have a friction force here. And I still have the weight of B pulling it vertically down. I kind of failed drawing it there, but it's going vertically down. Now, because the angle here doesn't change, the weight doesn't change, that means the normal force is not going to change, which also means that the friction force is not going to change. So we can bring over the fact that the friction force on B is equal to 7 newtons. That's still valid here. The only thing that changes is there's not a tension pulling left here, so there will be an acceleration to the right. So the way we actually solve that is we do sum of the forces along the ramp. In this case, it's not equal to 0. It's going to be equal to the mass times the acceleration along the ramp. But the sum of the forces just gives us T2 minus friction on block B minus weight of B times sine of 36.9. And again, it's not equal to 0. It's equal to the mass of block B times the acceleration of block B by Newton's second law. Now, the mass of block B is equal to the weight of block B divided by G. And so we can plug in both these values and we get 2.55 kilograms. And so we have 2.55 here. And if we're solving for AB, we just need to calculate this and then divide by 2.55. Now everything is known at this point, and so when we solve, we get an acceleration on block B of 3.43 meters per second squared. And the key idea now is that the acceleration of block B is tethered to the acceleration of block C. They're going to be the same. They're going to accelerate at the same rate. And so the acceleration of C is also 3.43 meters per second squared. And that's the final answer for part D.